We have discussed what FOL interpretations are, and next we are going to discuss what it takes for FOL sentences to be true on a given interpretation. Now, we are going to proceed in 3 steps. First, we are going to discuss what it takes for atomic sentences to be true on a given interpretation. Then we are going to look at complex sentences, but to the exclusion of quantified sentences. And then in the third step, we are going to look at quantified sentences and what it takes for quantified sentences to be true on an interpretation. Now, the good news is that the first 2 steps here, atomic sentences and complex sentences, are pretty straightforward. The bad news is that the third step, when we discuss quantified sentences, is pretty complex. So let's see how that goes. So what does it take for an atomic sentence to be true on a given interpretation? Suppose that R is an n-place predicate and A1 to AN are n names. Then the sentence that results from combining R with these n names is true on an interpretation I if and only if the ordered sequence of objects that this interpretation assigns to the names A1 to AN is an element of the interpretation that I assigns to R. Now, as a special case of this, let's think about the identity sign. A equals B is true on an interpretation I if and only if I assigns the same object to both A and B. Let's look at a couple examples to see how this works. So here on the left-hand side, you see an interpretation. The domain includes 2 objects, Anna and Berta. Then we have 3 sentence letters. Let's ignore them for now, they don't matter. The interpretation assigns Anna to the name A and Berta to the name B, meaning that A refers to Anna and B refers to Berta. And then our interpretation says that the predicate F applies to Anna and the predicate G applies to the ordered pair that has Berta as first member and Berta as second member. Now, on this interpretation, the sentence GAB is false. Why is that? Well, the name A refers to Anna and the name B refers to Berta, but the ordered pair that consists of Anna as first member and Berta as second member is not an element of the interpretation of G. So that's why GAB is false. The sentence GBB, however, is true. Why is that? Well, B refers to Berta, and the ordered pair that consists of Berta as first member and Berta as second member is indeed an element of the interpretation of G. So that's why GBB is true. Now, furthermore, A equals B is false, given that A and B refer to different objects, but A equals A and B equals B are true. Next, let's think about complex sentences. A conjunction A and B is true on an interpretation I if and only if both the first conjunct A and the second conjunct B are true on I. A disjunction A or B is true on an interpretation I if and only if either A or B is true on I. A negated sentence, not A, is true on an interpretation I if and only if A is not true on I. A conditional sentence, if A then B, is true on an interpretation I if and only if either A is false or B is true on I. And finally, a biconditional sentence, A if and only if B, is true on an interpretation I if and only if either both A and B are true on I or both A and B are not true on I. So all of this is pretty much as expected, knowing what we already know about the Boolean connectives. Now, the definition of the truth of quantified sentences on an interpretation is more complicated and we need to approach it in several steps. So first I'm going to introduce a new concept, the concept of a substitution instance of an interpretation. So let's start with an interpretation I. Let's suppose we have an interpretation I. Now, the interpretation IDC is just like the interpretation I, except that it refers to the object D by the name C. So if you look at this sequence of symbols here, the capital I followed by the edgy brackets and then D/C inside the brackets, that is the name for an interpretation. That whole thing refers to an interpretation. And what we know about this interpretation is that it is exactly like the interpretation I, except that it uses the name C to refer to the object D. So let's look at an example. Suppose this is our interpretation I. We've seen it before. The domain includes Anna and Berta. A refers to Anna, B refers to Berta, and so on and so forth. Now, the interpretation I, Berta, C that I've denoted down here, I, Berta, C, is just like I, except that it uses the name C to refer to Berta. The next important concept that we need to introduce is the concept of satisfaction. An object D satisfies the open formula A that has one or more occurrences of the variable x on an interpretation I, if and only if the sentence that results from replacing each occurrence of the variable x by means of a name C for the object D is true on the interpretation that uses the name C to refer to D. So that sounds pretty complicated, but the intuitive concept is actually pretty straightforward. So for example, the object D satisfies the open formula fx on interpretation I if the sentence fc is true on the interpretation IDC, which uses the name C to refer to object D. An easy and intuitive way to think about it is that D satisfies fx on interpretation I just in case fc is a true sentence, assuming that C refers to D. Now, with these concepts of a substitution instance and satisfaction in hand, we now can go on and define what it takes for quantified sentences to be true on an interpretation. Let's start with existentially quantified sentences. So the existentially quantified sentence, there is an x such that ax is true on an interpretation I if and only if some object in the domain satisfies the open formula ax, which you see embedded within the scope of the quantifier. So given what we just said about satisfaction, that means that there is an x such that ax is true on an interpretation I, if and only if for some object D in the domain of I, if you use the name C to refer to D, then the sentence AC that uses the name C in place of the variable x is a true sentence. So let's just look at a couple examples. So here we have our toy interpretation again. Our domain includes two objects, Anna and Berta. We use the name A to refer to Anna and the name B to refer to Berta. And then the interpretation of F includes only Anna, and the interpretation of the predicate G includes the ordered pair that has Berta as first member and Berta as second member. Now, on this interpretation, the sentence, there is an x, fx, is true. And why is that? Well, Anna satisfies the open formula fx. And why is that? Well, if we substitute a for the variable x in the open formula fx, the result is the sentence fa, and that sentence is true on our interpretation I. Now, as a second example, the sentence, there is an x such that gax is false, given that A refers to Anna, and there's no ordered pair in the interpretation of G that has Anna as first member. However, the sentence, there is an x such that GBX is true. And why is that? Well, Berda satisfies the open formula GBX, given that the sentence GBB is true, where we substitute B for the variable x in the open formula GBX. And then to look at a final example, the sentence, there is an x such that x doesn't equal x is false. Given that neither Anna nor Berda satisfies the open formula, it's not the case that x equals x. Anna equals Anna and Berda equals Berda. Now what about universally quantified sentences? The universally quantified sentences for all x ax is true on an interpretation I, if and only if every object in the domain satisfies the open formula ax that appears in the scope of the quantifier. Now, given what we just said about satisfaction, that means that for all x ax is true on an interpretation I, if and only if for every object in the domain of I, if you use the name C to refer to it, then AC is a true sentence, where AC here is just like our open formula, except that it has the name C at every place where the open formula had the variable x. So here are a couple of examples to illustrate this idea. We have the very same interpretation again. The domain includes Anna and Berda. We use A to refer to Anna and B to refer to Berda. And the interpretation of the predicate F includes only Anna, and the interpretation of the predicate G includes the ordered pair that has Berda as first member and Berda as second member. On this interpretation, the sentence all x are F is false. And why is that? Well, Berda does not satisfy the open formula fx, since the sentence fb is a false sentence. As a second example, the sentence for all x gax is false, and the sentence for all x gbx is also false, given that Anna does not satisfy the open formula gax and also does not satisfy the open formula gbx. And then to give you a final example, the sentence for all x equals x is true.